Welcome back. So I wanted to create this video to talk about the relationship between pointers and structs, both pointers of structs and pointers within structs, and how they can be combined to create very flexible data structures and more powerful programs for us. Like any data type, we can declare pointers to our custom struct types to do the things we've been doing with pointers, either dynamically allocate or update variables using those pointers. So we have, for example, our declared struct for student data that we've been using over and over again. And while we've declared arrays of structs, we can also declare a pointer to a struct. So, for example, there is student data pointer as a pointer of that type, and a separate one as well. We can then do dynamic memory allocation. So that same malloc function call that we've been doing for ints and other types works exactly the same when for a structure type, we say we want to allocate 15 of those student data structs for us. And so we have to pass in both the number 15 as well as the size of the individual structure for us. And it'll allocate the right number of bytes for us. We don't even need to know what that right number of byte is, but we need to tell it that it's each of those elements is of size student data. So in that sense, the pointer works exactly like our int pointers for our structures. And similarly, if we want to actually grab the address of some other variable, be it an element in an array or just a single scalar variable of that type, we can also use that address, that ampersand operator, and store that result as a pointer. Once we have those pointer types, though, we have to be a little bit careful with our syntax. We have to dereference or follow the pointer first, and then we can use the data access operator, that dot operator. So syntactically, it would look like the following, where we want to grab a quiz value from a pointer to that student structure. We have those parentheses here to indicate we're actually following that pointer first. So we followed that pointer. We followed the pointer. We have the value of that structure pointed to at that address location. Then we have the dot operator. And I think it's fair to say you will see plenty of code bases that will still use that syntax. There's nothing wrong with that syntax. It is valid. It's kind of messy, certainly once you start to have pointers to pointers and things like that, but it is valid C syntax here. It's such a common and relatively awkward thing to do in our C programs that there is a second member access operator for structures, specifically for when working with pointers. You can call this the arrow operator. And those two lines of code with the reference followed by the dot versus the arrow operator are equivalent to each other. It's a funny thing, right? When you have a regular structure, you use the dot operator. When you have a pointer to a structure, you use the arrow operator, but they are doing the same exact thing. So that's the member access operator when we are just working with pointers. And the example I wanted to show you here is effectively the same exact example as our previous video we had, just very slightly updated to instead use pointers for some of the things we like to use pointers for. The structure is still exactly the same. Um, our print student is a good example of using that member access operator. So we've actually modified the function prototype to, instead of taking an individual student structure as an input, there's a pointer to a variable of type student structure as input. And now when we're wanting to print the first name or the section or the quiz scores or what have you, we're not using the dot operator as the prior example had, we're using that arrow operator. It's functionally the same. There is arguably, it's quite arguable, some performance benefit in doing it this way with pointers, because what was happening previously, right? We have this variable of type student data, and we're having to copy that whole variable over to be able to then operate on it in this print student. Well, these structures can get quite large. That's a lot of potential copying going on. Now, when we have this pointer version of the same function, we're not passing the student structure anywhere. We're passing that address. We're passing that pointer. We're passing 64 bits to that function and then operating on it by following those pointers. I say arguably potentially more efficient is for the first reason, compilers are very efficient. So I trust my compiler to do a better job of optimizing than worrying about using a pointer here to save some potential storage of memory. But that is an equivalent function, just using a pointer versus using the actual variable of that type. Likewise, before we had declared a static array of that student data, and now it's just a dynamically allocated array. Still, it's num students, it's 100 students. We can do our realloc, our calloc, our free, and all that stuff will work as one would intend. Our reading of the files were still the same as before. And now here we're doing our initialization of that. We actually, because we did allocate an array with that array pointer equivalence, we still could have used the array syntax and that would have still been fine. We could have done students of I dot value. That would have actually still been valid and neither right nor wrong to do it that way. But just to illustrate using pointers instead, here we create a local pointer to kind of iterate through the array, and we explicitly set it to the address of whatever students of I is. If I were writing this code outside of this, context here, I probably wouldn't do that. I know that I've allocated 100 students. That's an array of 100 students. I would probably just use the array operator because I think it's a little bit cleaner. But if we have just an individual pointer and we're actually updating the individual pointer, then we would be using that arrow operator to do so. And likewise, we do have that pointer array equivalent. So when we call print students or sort students, we can just pass it that pointer. But it is the same effectively as passing that array when we had the array example here. So the main difference is this operator we have, this arrow operator versus the dot operator that we previously had. So that's an example of pointers to structs. And it's just something you learn. You'll see examples, and you'll get a compiler error when you don't use the arrow operator and instead use the dot operator, and you'll be able to fix it pretty quickly when you see that. This is slightly different than the topic of pointers in structs because structs themselves can certainly also just include pointers themselves. Instead of having had statically allocated arrays for first and last names, it would have been equally valid to instead have had car star pointers for first name and last name. And then we would have had to have done dynamic memory allocation if we wanted to actually store values for the first name and last name there. If it's a string type, we don't necessarily have to store the length of first name and last name because we can always calculate the length of string using string length function. But for other dynamic array types, we would have to store the length associated with it. So it's perfectly valid, allows you to dynamically resize the size of the structure itself. But the slight downside of that resizing of the internals of that structure itself is when we were going to do those copy operations, right? Temp student equals, or student data temp equals student one, like we saw in the sort example. That copy is a so-called shallow copy. We're copying all the elements of the structure, but now those elements would be pointers. They wouldn't actually be whatever is getting pointed to by those pointers. And sometimes you actually do need to copy that data as well. And so if that's the case, and you need to copy not just the pointer to first name, you need to copy the actual data pointed to by first name, you would then need to write your own copy function. That's a so-called shallow versus a deep copy. It's not necessarily a hard thing to do, but it would be kind of a bespoke copy function for your particular custom structure that happens to have pointers. But that's maybe the downside of doing it. The upside of having pointers in our structure is we can actually do some pretty clever things. And with a little bit of clever syntax, we can actually have a member of the struct be a pointer variable to that type itself. So syntactically, there's a little bit of trick going on here where we're doing our type def struct, and we're still naming what that struct is going to be at this point of struct int node s. We have some value data type that we are storing here. And then we can actually have a pointer to another variable of that type, struct int node s. The entire thing being called the structure of type int node. So that's a pointer to a variable of the same type of structure. And there's a very specific reason we would want to have that in our program is to be able to connect different variables of the same data type to each other in ways that are more flexible than just having a statically or dynamically allocated array where everything is kind of contiguous with each other in memory. Visually, what we would have here is if we allocate a single pointer and refer to that as head, that is now a pointer and an address corresponding to an allocated value as well as an allocated pointer. And then as we continue to allocate more, we can use that next component to actually point to those next values that could be allocated all over the place. They don't have to be consecutive to each other in memory. They can be allocated at completely different times, and we would just be following that pointer to go from item to item to item. The resulting data structure in this case is known as a singly linked list or just a linked list. It does allow us to be very clever in terms of how we are adding and removing entries because we're no longer dealing with that contiguous or consecutive array in memory. We had that vector type, which is also allows for some flexibility, but there we saw when we wanted to insert something into the vector, we had to grow the vector, and then we had to kind of manually copy everything over. Here in our linked list, if we want to insert something into our linked list, we would need to allocate a new element in our linked list. We would just need to update our pointers. We wouldn't need to actually copy anything over at that point. How do you sort like, a doubly linked list has become such a kind of cliche interview questions, even for undergrads who are on your very first, internship interview. Um, Basically, the question is checking if you've taken a data structures course, but you'll get that question even before you've even taken a data structures course. We can give it a try with our existing knowledge of C. We'll start with this code base, which is a data structure that kind of points to an element of the same type of structure. And then we're going to show how we can kind of link the data together. And then the main difference is how we do our compare function and how we do our kind of temp swap operation. We have to make sure our pointers are consistent with each other when we do that. Let's give it a try, and if we fail, we fail. But I think we should be able to figure it out. So we need to start with our actual linked list. Let me just go and kind of copy paste that from the PowerPoint slide here, where we are defining our linked list structure here, where there's going to be an actual value and then a pointer associated with it. And I think it is important to kind of visualize what we have here. So it was on the slide. Let's make sure that's clear, that it's a little bit different than our int vector, which was also just a single value. One of those was just an integer, and the other one is now a pointer. Pointer's got to point somewhere, but we like to visualize that it's actually just storing an address. It's not physically pointing anywhere, but when we have a pointer, we know we're storing an address. It should correspond to some location in memory. We'll start with that. So we have that structure defined. We need to actually then build up an array of these, or a sequence of these. Let's just start with like 25 or something like that. Where we are allocating those nodes at different times in our program. For our purposes here, we're kind of just allocating them all in the very beginning, but we're going to allocate our nodes as we go and update the pointers from node to node as we go. That example on the slide had this idea of a head pointer. That is specific to this concept of a linked list. The idea being you have this array of data that you've allocated, and you have a pointer somewhere to keep track of where the beginning of it is. That's our head pointer. And that is just kind of a standalone pointer that is just pointing to that first element that we have in our array here, or our element here. So we could actually do this with an array. I'll even make that note. This could be an array. But if we made it just a statically or dynamically allocated array, that kind of defeats the point. So defeats the point of having a linked list if we just do a statically allocated array. But we can allocate them one by one. Using our malloc call. Remember, it's going to return a variable of that type. And there's our syntax. It should look very similar to our previous malloc calls, where we're saying, hey, allocate me one element of that type. And we have to actually return that somewhere, I guess, right? So we don't want to store that as the head. We need to have some other pointer to keep track of that value. We'll call that, I don't know, current node. That's the current node we're currently going to allocate here. And that would need to be a pointer like this one is already a pointer. So current node could then be stored as a result. We're going to allocate one node. We need to initialize it to some value, so that's the easy part. Now, remember, that's a pointer. We're going to use that arrow operator for the value, and it's just something, I don't know, rand mod 100. Who cares what it is? And there's also that second component. That's the next. What's the next thing we are pointing to? We don't know what that is yet. We haven't created it. But we should probably still initialize it accordingly. So there's our next thing we're initializing here. So we have this head. We haven't actually, let's see if we can erase this here. We haven't actually connected that to anything yet. Likewise, we haven't connected this to anything yet. But what we have done is created a pointer to that. And that part, I'm kind of playing a little fast and loose with where the pointers are actually pointing, but that's our current node. And we know it's a variable storing an address, but that arrow shows that it's pointing to it. If this is the first one we're allocating, and this one, that next pointer is currently going, question mark, question mark, question mark. It's null. It's not really pointing anywhere. It's just off to abandon. If this is our very first one, that's what that head pointer was for. We would want to point that there. There's more than one way we could have done this. This approach will actually work, where we're saying next equals null. If this is our first one, if this is our first pointer, then let's actually set it to it. And it's a pointer, right? It's not head next or anything like that. Just we're pointing to that current node. Head itself is just a pointer. We didn't allocate anything for it. We have just a pointer for it. It's now going to point to that current node. That line of code is what added this arrow that we have here. We got to actually connect the nodes to each other. So every time around we are allocating a new node, we got to kind of keep track of which one is which. So we're done allocating. For the next time around, we want to say previous node equals current node, right? Previous node is going to be a pointer to the one we just allocated. And now when we want to now allocate a new node, what's going to happen when we go through the loop, right? Head only changes the first time. Head is fixed. Current node gets allocated each time. So the pointer itself doesn't necessarily get moved, but another way to think about that is we've done it. We've gone through the loop once. Current node is the result of a new malloc call. So current node now points here with a new val. There we go, looking a little bit more strucky here. And with a new next. And now we got to hook things up, right? Now this pointer, which was next, which is initialized to point to nothing, now needs to point to this. It's a little messy, but if you're drawing it out, we can logically kind of walk through it, right? We've allocated a new current node. We actually still have a previous node that's pointing to that. So previous node's next could be set to be equal to current node. So previous node is current node. If we're not on that first one, it won't work if we're on the first one because there is no previous node yet. But in this case, previous node next can be set to current node. And that should set up our linked list. And that, as we continue to allocate new ones, what'll happen? Current node, every time we go through the loop, we've allocated. Previous node, after we've allocated, gets updated to point to this one. And we continue that, right? Now current node, after the next time through the loop, is going to point to this one. And once we've done that, we can actually then update that pointer. So we have that link. And that is the linking of the list that's happening here. A special pointer to keep track of where we're starting. If it was an array, you could just do array index of 0. But here, we just, for now, it's not even of 0. It's just a series of linked together items that we have here. And then we can follow. We can go from head to head next to next to next. Eventually, though, we'll get to one for which we never actually updated it because we're done with the loop. And then we should find our null pointer. So our code that's looking at those should be aware of eventually this is going to end because we've reached the point where we've gotten to a null pointer. And what do we do next, right? We've declared, we think we've created this data structure. Let's print it out, right? So we've allocated our data structure here. Let's call print, I know it doesn't exist yet, print nodes, and we would pass it like that head pointer. Get started, print that print node here. We can do the declaration of that function after we've declared the structure itself. So print nodes, and we can see we have that pointer. It should make our life a little bit easier here. We can do the array type approach, but we actually don't need to anymore. We have a linked list. We can start with our head. Actually, we can do this with a while loop, or with a for loop, which would be kind of fun. We'll do the while loop version, then I'll show you the for loop version. And let's keep a little counter here as well. While our pointer is not null. Keep going until our pointer is not null. And there isn't that much to print out about our node, but what can we do? Node I. What else is interesting about the node? Well, let's print out the actual pointer. I don't know, where are we in memory? It's always good to know where we are. The actual value, if we're going to do any sorting here, we would need to know what the value is. And that's pointer value. And it would also be another separate pointer would be what is it pointing to next. Okay, that's for our first time through the loop, pointer is head. We now need to, as we go through the loop, update where that's pointing to. So this is a temporary pointer that starts here, needs to go to the next one, and to the next one, and to the next one. So that pointer, it's not like pointer plus plus, that will not work for this circumstance, but the pointer needs to be updated by whatever that next was. That's the whole point of having a linked list. We have the pointer to this element, we then connect to the next one, to the next one, to the one after that. Print nodes should work. Okay. And it's a lot of addresses, so there's only so much we can do with it. But it's addresses, each of which have values and pointing to the next location. And that next location is pointing to is in fact the address in which that next one is stored. So the linking is working. It's not actual arrows, right, in our diagram, but it's actual addresses being stored in memory. And we get the results we would hope here. With probably the final one it's printing out as nil, as a null pointer, as an uninitialized pointer, as expected for this case. This code is perfectly fine. I'll leave it commented here that this is like the while loop version of it, but we can also do a for loop version. As with all of our for versus while loops, one is not better than the other. But our for loop, right? For our loop iterator pointer being initialized, that's what our initialization was. Pointer is set to head. And it's a local variable to this loop, which is okay. We're only using it inside this loop. When are we done, right? Pointer, not pointer less than 7 or something like that. Pointers keep going until the pointer's null. And then when do we initialize? Pointer equals pointer next. And then all of this code, well, we don't need the plus plus anymore. It's going to be unhappy about I. We can figure that out in a second here. And you can initialize multiple. I don't know if I would recommend this, but you can initialize multiple things. For I equals 0, we start with. We have to declare it into I equals 0. Oh, it's unhappy about that. So let's do it without that multiple declaration. And we'll still have that here. And then each time through the loop, we're both updating our pointer. Oh, it's very unhappy about that. So we'll just not try to do two things at once. We'll just set I equals 0 and then go back to our I plus plus example here. And that's just an example of now ignoring the I part, which was just there to kind of print an index. If we were using an array, we would loop through it like a proper for loop. But in this case, this is a valid for loop, right? Initializing our pointer to be the head of the list, continuing until that pointer is garbage or reaching a null pointer scenario where it's not pointing to anything valid. And that's our increment scenario here, right? Which is next, we're done with this loop, iteration of the loop. Next iteration, we do so by setting pointer equal to the next pointer. Yeah, we should get the same exact result we have here. We know how this is going to go, right? It's print, sort, print. When we sort things, even if it's a linked list, I think it can still be helpful to have the length information encoded. It's probably not necessary. But I think it'll reduce the number of lines of code where we're not having to constantly checking for null pointers. We know there's this many number of nodes. Slightly cheating. This function hasn't been declared yet, so we know we're going to need to have some sort of sort nodes function. It's a little tricky compared to what we've done, right? In the past, we've sorted arrays. It's always been arrays. Here we're sorting a list. We're sorting an array. The array doesn't change. The elements in the array doesn't change. Here we're sorting a list pointed to by that head pointer that we have here. The head pointer itself is going to change. Unless it just so happens that first element is the one that should be at the beginning of the array, that the element itself is going to change. So it's a little tricky in that we do want to sort and change the value of that head pointer. We can do it multiple ways. We can return a new head pointer, or we could pass the head pointer itself a pointer to that head pointer because we're going to be updating that head pointer in this function. One approach isn't necessarily better than the other. This syntax is going to be especially yucky, so let's go with it. So sort nodes, now it's going to be a pointer to a pointer because we're going to update it. And we're also passing that length information so we know when we're done with the array, and we can use simple for loops and not have pretty ugly looking while loops for our implementations. So we can still use a very bubble sort looking bubble sort, I think would be a nicer way to do it. It's not wrong or right, but this is how I would do it. So your basic structure of the for loops should not change much. So we can always write that if we know we're doing bubble sort. Now it gets a little tricky though. So now we need to know we're going to be updating this pointers via whether or not the values pointed to in that structure is greater than the other one. So we know there's a temp and then there's a swap operation, but because now of our input here, this is going to be fun. So let's give it a try. So let's create. We know we're going to want to update head eventually here. We start off. We want to start at the start of the array. We didn't have to do that before start of the list because we had an array. We know it always starts at 0. Here we're starting at the head pointer, which may actually be changing here. We have a pointer to it here. We're going to do our swap, right? We're looking at I or J versus J plus 1 like we've been doing for all of ours. We need to declare some, we can call it A and B. J plus 1 is going to be kind of hard to encode as a variable name. So that's our current one we're looking at. This is the next one we're looking at. Well, where is it? It's where the current one's looking at next. That's our J and J plus 1 if it were an array, but it's not an array. It's our linked list here. Now we have our J and J plus 1. The actual comparison code, at least for numeric sorting in order, is exactly the same. We're just now accessing the individual elements here. And when we do that, now we need a temp that we need to actually swap those pointers. And there's a little bit of extra bookkeeping, right? Because we have to make sure that the nexts themselves are getting updated. I'll try to draw this out, but it's a little complicated in that, it's not just the values themselves. We need to make sure the pointers themselves are getting swapped. Another way to think about that is we have, let's look at this one and this one here with all of this stuff up here not being valid anymore because we don't have current node. That was when we were creating it, so those pointers don't mean anything anymore. But we do have those two pointers. And let's assume that this one is somewhere in the middle, is probably easier to visualize. And we have what we were calling P1 and P2. Well, with our array sorts, what were we doing, right? We were trying to take the values and kind of replace the values. With our linked list, we don't actually have to copy the values at all. We just have to make sure we update the pointers. So if we did our numeric comparison and realize that, in fact, P1 should be on the other side of P2, and we should do that swap operation. With our linked list structure, that's all we have to do. We have to make sure that now what was pointing to P1 is instead now pointing to P2, because that's actually the next one. And what P1 was pointing to is now whatever P2 was pointing to, and now what P2 is pointing to is in fact P1. Right? We're swapping the pointers. We're not actually swapping any of the variables. We're not moving anything in memory. We're just updating the addresses that this list of values maybe be in a certain order in memory, but we're swapping the pointers and how we're traversing those addresses, what next means for each element, and the end result is something that is sorted based on how the addresses are connecting to each other here. So P2 next is P1. P1 next is temp, and then we actually have to update that H pointer, which probably could have called it something better. So that one now, that was the third one. We have to update those 3 pointers that we have here. H is, we have to go to the next one. We have to go to J plus 1 here, and that's why it's a little bit, J tells us how many times we have to iterate through this bubble sort, but it doesn't actually increment where H is pointing to, so we have to actually update H. H is H next, but syntactically that's going to be ugly. It's the address of H and where that's pointing to next. Okay, so it's H next, and then following that pointer, and then taking the address of that. That's ugly syntax. don't worry about that. But conceptually, if you were following what was happening on this diagram, you're in pretty good shape for understanding how linked lists are working. Let's give it a go. There's a lot printing out here, and there's a lot of nodes. So there's our original array being printed out. And then there is our, I'm having trouble just scrolling through all the data here. Then there's our new array being printed out. We can see it is in sorted order, right? The variables themselves are in sorted order. But what I think is kind of cool is before we did the sorting, you may disagree with me on what is cool or not. The memory was also in sorted order because we were allocating one after the other after the other. And you're not guaranteed for it to be in sorted order, but unless there's a lot of memory fragmentation going on, it's probably going to be one after the other after the other. When we've done the sort now, the variables are in sorted order, like the values themselves, but the actual memory locations are where they were originally. The node that held the value of 86 is in the same location it was before. And it's just the pointers themselves that have been updated to be pointing to those new locations in memory. So we've been able to sort our array without actually touching anything that is in our memory itself. We've allocated it, they're sitting there where they are. If we wanted to insert, although I don't want to get into that, insert a new value into that linked list, we'd allocate a new element of that linked list, and we would just update our pointers accordingly to get that new linked list without having to move anything around in our list structure itself. That's an advanced example. One of the programming practices involves pointers inside your structures. It's challenging. I won't deny that. You just have to kind of draw out that data structure for like the census records that you're parsing and looking at, and making sure things point to where they need to point to. Because it's that we're not sorting it in that sense, but that same structure then needs to be updated so that it's always pointing to something valid. And if you're always pointing to something valid, whether or not you have it exactly correct or not, you should at least be able to use those print functions to kind of debug what it's doing to get something that's reasonably close to correct. And then from there, figure out what part are you missing and why is it not exactly matching the expected output of it. Good luck with that example and all the examples for this programming practice. I believe in you, and we're almost done, and you can absolutely do it. Good luck.